Welcome back to this course in polymer chemistry, and in this lecture we will continue our discussion on polymer stereochemistry and coordination polymers, which we began in the last lecture. Now, in last lecture we had discussed this page, and remember we discussed this, that if this active chain end in a propagating chain, polymer chain, if this carbon is a radical or it is a anion or cation with a counter ion which is not strongly binded. If the counter ion for anionic or cationic case they are free, then what happens, this carbon atom is a planar molecule, and then when the next monomer approach, it can approach from either side. So, the configuration of this carbon is determined by the configuration of the penultimate carbon, with this case this carbon, and obviously it is always preferred that this bulky group will be, or the group substituent group will be the other side of the R group, which is in the this penultimate carbon, which means syn-diatective polymers will be always preferred. Syn-diatective addition will be always preferred than a isotactic addition, and this preference will always go up if we increase the temperature. Now, how to synthesize a highly isotactic, and we also said that if we increase the temperature, obviously the tendency for syn-diatective and isotactic will be significant. So, we will going to get a atactic polymer at higher temperature. So, basically we know how to get syn-diatectic polymer and we know how to get a atactic polymer. So, how to get a highly isotactic polymers? Now, we can get a highly isotactic polymers if we do a ionic polymerization such that we have a very strong coordination between the counter ion, the monomer, the incoming monomer, and the active chain end, which could be a cation or an anion. So, if we carry out a ionic polymerization where we have a strong coordination between the counter ion with the cationic or anionic chain end and the incoming monomer, then the approach will be from always from a same side of the same side. So, we will get a isotactic polymerization. Now, how do you get or create a conditions where this thing, this coordination, strong coordination between the active chain end, the monomer and the counter ion happen? Now, if we have a monomer which have a polar group as in the substituents, like say you have a methyl methacrylate or a ether group in the backbone where this is a polar molecule. So, this can actually coordinate with a cation in this case. So, monomers with polar groups in the substituent will help in coordinating with the counter ion and the monomer, the incoming monomer. Now, it is said that if the monomers are, if the chain end, the active chain end, whether it is a cation or an anion, if they are free, if the counter ion and the active chain end they are free, then we have seen what are the types of stereochemistry we are going to get, but if they are very tightly bound, then they can coordinate. Now, how can we make sure that this counter ion and the active chain end are tightly bound? If we can carry out the reaction in a very non-polar medium like hydrocarbon, and if we have a counter ion which is small in size, so that they will be tightly bound, for example, like lithium, and if we can carry out this reaction at low temperature, what happen then? We can get a coordination, strong coordination between monomers and the incoming the active chain end and the counter ion. Now, let us take example of methyl methacrylate. If we do the reaction, if we take a methyl methacrylate and do a reaction with an anionic initiator, say for example butyl lithium in say toluene at lower temperature. So, if we consider say N butyl lithium as a initiator and toluene as your medium, non-polar medium, and say minus 78 degree temperature. So, this condition will satisfy that the carbon ion chain end and the lithium counter ion are tightly bound, strongly bind each other, and if that is the case, then you can imagine a situation like this, where because of resonance this ionic charge is distributed we can in the three atom. So, this counter ion help in strong coordination between the active chain end and the polar substituent of the another monomer residues present in the chain. Now, if such thing happen, then what happen, one of the side is blocked. So, the new monomer, incoming monomer can approach from only one single side. So, there is a loose cyclic intermediate formation and one side is blocked by lithium. So, monomer can approach, the incoming monomer can approach only from a single side and always producing a isotactic polymer. So, if you do this reaction in lower temperature non-polar medium with a lithium plus type small counter ion, you can get highly isotactic polymers. Now, if you can do the same thing with isobutyl vinyl ether and make a cationic polymerization with say BF3 H2O, BF3 etherate and H2O type initiator, then you have a cationic group, and again you have now a anionic counter ion which are tightly bound because you are carrying out this is in a non-polar medium. Again you can think of a similar MMA type situation where in this case the counter ion is actually doing a strong coordination between there is this monomer substituent and the incoming monomer, forming this type of intermediates, and again one of the sides is blocked. So, the monomer incoming monomer can add to the chain from only single side and you can get a isotactic polymer always. So, if we look at some data, let us consider methyl methacrylate as this is a normal butyl lithium in toluene at minus 80 degrees 78 degrees centigrade. That is the example I gave in the last page, that will produce isotactic polymethyl methacrylate. Look, if we have the same polymerization, same temperature, same initiator, but if you increase the polarity of the medium. Now, obviously, if you increase the polarity of the medium, THF is a highly polar solvent. So, the counter ion is not tightly bound or strongly bound with the active anion end. They are free ion, the lithium ion is a free ion, which means the chain end has a planar geometry, and as we discussed it will give you a syndialectic polymer, syndialectic methyl methacrylate. Now, if you increase the temperature, if you do the same reaction with butyl lithium in THF and do it in a much higher temperature, then you are going to get a mixture of isotactic and syndialectic component in the polymers. We are going to get a atactic polymerization. This is example of cationic polymerization. We just gave BF3 etherate in propane at minus 60 degrees centigrade. That is the example, cationic example we just gave, and which gives you a isotactic polymer. So, what we know that radical polymerization will always give preferably syndialectic polymers, and this get dominated to decrease the temperature. Now, if you for ionic polymerization, if we do polymerization in condition where the ionic chain end and the counter ion they are present as a free ion, then they will behave same as radical polymerization. And if we do the reaction in conditions so that the counter ion is strongly bound with the active chain end, then what happened and that which we get if we do a reaction in a non-polar medium at lower temperature and with a small counter ion, then there would be a possibility of a strong coordination between the monomer and the active chain end and the counter ion, which will make sure that the monomer incoming monomer gets into the chain from one side, which will produce a isotactic polymerization, isotactic polymers. So, we know that what are the strategies we should do to synthesize isotactic, synthatic and atactic polymerization. Now, let us see how do you analyze these polymers. Now, let us consider a simple molecule, again same thing. Now, if we write two asymmetric pair of carbon atom. Now, this is the horizontal line is your polymer backbone, and this lines gives you the configuration of the carbon atom. So, this in this case both the carbon atom, the asymmetric carbon atom has same configuration. So, we call this as a mesodiode, and if they are in opposite direction, then we call this as a racemic diode. We write M, we write R for this. Now, diatacticity, this term diatacticity is defined as the fraction of pairs, these are pairs, this is another pair. So, fraction of pairs of adjacent repeat unit are in a particular stereochemistry, say isotactic or syndiatactic. So, if we write M is the fraction of pair adjacent repeat units that are present in a isotactic geometry, and R is the fraction of pairs of adjacent repeat units that are present in a syndiatactic geometry, and of course, M plus R would be equals to 1. Now, sometimes few people write this as a gives you isotactic. So, they write as I, and racemic which gives a syndiatactic, they write at a small s as well. Now, we also can imagine triads where we are talking about three series center adjacent to each other, like in this case you have a meso pair, another meso pair. So, which actually gives you a isotactic polymers, and we write this as MM. Okay. So, meso pair, another meso pair. So, what will be, this is a racemic pair and this is also another racemic pair. So, gives you right RR, and this gives you a syndiotactic E arrangement. Now, in this case give another possibility where you have a mesodiode, another is a racemic diode. So, you can have a meso MR, which gives you a heterotactic or atactic stereo arrangement. Again we define similar way, AMM is the fraction of these 3 and RR is fraction of syntactic triad and AMR is the fraction of heterotactic triad. So, we can write MM plus RR plus MR is equal to again 1, and sometimes some people write this is gives you isotactic. So, they write I, they write this is syntactic. So, they write S, and this is heterotactic, they write H. Now, we can easily write other from this expression, you can do yourself plus 0.5 MR and R as RR plus 0.5 MR. Now, for isotactic or atactic polymer, both fraction for R will be equals to half. So, half of the dyads will be in meso form, half of the would be in racemic form. So, basically it is a 50-50 mixture of isotactic polymers, dyads and racemic dyads, which is a completely atactic polymer. If you have a isotactic polymer, then AM and MM both the dyad and triad would be equals to 1, and if have a syn diatactic, then R and RR also will be 1. Now, in case of atactic, you can also write MM and RR is 1/4, whereas MR, if you have this 50-50, then obviously this MR combination of M and R triad will be half. So, you can write this. So, what we can do, we can identify this M and R from spectroscopic techniques like NMR. We can use NMR techniques to find out the fraction of N, R or MR in the all this we can find out quantitatively from an NMR experiment, and if we can find out this, we will be able to determine what is the extent of isotoxicity or syntacticity in the polymer. If AM is greater than 1/4, so as the MM triad, then obviously it is predominantly towards this is going towards isotactics. It is more isotactic rather than syn diatactic. If R is greater than 2.5 and RR greater than 1/4, then it is towards a syn diatactic, that you can yourself conceive this is what happens. If it is and there is a mixture, then it is always a isotactic polymerization. So, what these are the so we can what we can do, we can take the polymer which we synthesized and get a quantitative NMR done, and from that we can get the values of M, this one MM, R and R this we can get, and from that the values for the individual values we can actually estimate, or we can predict or even quantitatively get the amount of say tacticity which is the R fraction, which is the M fraction in the polymer itself. Now, what we will do, we will go and move to the next topic of Ziegler-Natta polymerization or coordination polymerization. Now, it was first started around mid 1950s, where the first Ziegler scientist in Germany, he was doing ethylene polymerization, So, ethylene and in presence of trialkyl aluminum, say for example, R3Al, at high temperature plus high pressure, you only got oligomers. So, oligopolyethylene or oligoethylenes, a maximum molecular weight of maximum MW of around 5000. So, he was carrying out a polymerization reaction of ethylene in presence of a alkyl aluminum, trialkyl aluminum, and at high temperature and high pressure he only got a oligomeric species, not a polymeric species. What happened when he added with this alkyl aluminum plus some transition metal compounds, when he added, then he even at low temperature, say like low temperature means 50 to 100 degrees centigrade, and at low pressure he got very high molecular weight polyethylene. So, basically only what is the change here? It is only the change of addition of transition metal compounds along with this alkyl aluminum. Then it was dramatically, the polymerization nature was dramatically changed. You get a very high molecular weight polyethylene. Now, this polyethylene is not branched like the polyethylene we discussed while discussion on radical polymerization, that in case of radical polymerization you get polyethylenes which are branched because of chain transfer to polymers, as we discussed, you recall from our discussion on chain transfer on radical polymerization. In this case they are not branched, they are linear high molecular weight polyethylene, and that can be achieved even at low temperature, which is very achievable or very comfortable temperature 50 degree to 100 degree centigrade at even a normal to low temperature, low pressure. Now, what happened, the same sort of catalyst was used by Natta. He was from Italy. What he used, instead of ethylene, he has taken say alpha olefin, say in this case propylene, and used the same sort of catalyst, alkyl aluminum plus transition metal compounds. Now, what he got? He got high molecular weight polypropylene definitely. In addition, what he found that was very stereoregular, stereoselective. Depending upon exact polymeric condition, it could be a completely isotactic or syn diatectic, depending upon the exact condition. But what he found, that it not only gives high molecular weight polypropylene, but it also gives very high stereoselectivity, whether it is a isotactic, completely isotactic, or syn diatectic. Now, these two has discoveries has a tremendous effect in polymer science, and even at nowadays say more than 30 to 40% of the carbon-carbon, the polymers which are made from carbon-carbon double bond, polymers which are made from carbon-carbon double bonds, they are synthesized by this coordination polymerization technique. So, imagine what is the tremendous effect it has, this discovery by Ziegler and Natta has made a huge importance in polymer chemistry, which has given as recognition to them in 1963. They are jointly awarded the Nobel Prize in Chemistry. Now, later on the large number of catalyst was developed, and basically what happened basically it is the combination of again the similar type of compounds, and there has been lot of research happened in this field, and most cases are organometallic compounds. So, organo compounds or hydride of a group 1 to 3 metal plus a halide or other compounds, other derivatives of group 4 to 8 transition metals. So, basically these are the this is you have to take one from here and one from here and constitute the catalyst, which generically called Ziegler-Natta initiator or Ziegler-Natta catalyst. For example, we can choose from this set we can choose say triethyl aluminum or diethyl aluminum chloride or diethyl zinc, and from these we can mainly use titanium chloride, tetrachloride, trichloride, vanadium chloride. We can use so many things, and these mixture take one from here, one from here, and constitute the Ziegler-Natta initiators. Until 2000, more than 95% of the Ziegler-Natta polymerization used a combination of this sort of catalyst before the discovery of the Metallocene catalyst, where instead of transition metal catalyst, Metallocenes are used as a catalyst along with a co-initiator, which we will discuss in a minute. Now, most of the examples of Ziegler-Natta catalyst, let us put it as Zn, are titanium, are from these two, say titanium dichloride or 2AlCl, or say titanium chloride plus 82 3, and most of the important industrial polymers are made from these, and this is the original polymer catalyst combination used by Ziegler. And what happened when these things are mixed, TiCl4 and triethyl aluminum, they are taken in a non-polar solvent and they are mixed. Now, it produces titanium trichloride, and this. Now, this when you mix these two, as it was mixed by Ziegler, what happened, this forms a beta form of titanium chloride, which is brown in color. Now, that this particular catalyst form, beta form of titanium dichloride does not have very high selectivity. What Natta found, that instead of using beta, other forms of titanium chloride like alpha or delta or gamma form of titanium trichloride, if you use this sort of trichloride, then you get a very high stereospecificity, very high amount of isotacticity in this case. Now, what happened, these two are generally, when the polymerization made, these two polymers are mixed and ball milled, that means mechanically grounded. So, that also increases the surface area of this catalyst. We will see in a minute how the surface area actually is important for this catalyst, and also it's actually help in increase the activity of the polymerization. Sometimes during the development of catalyst, these titanium trichloride or tetrachloride, they are used along with a support like say magnesium chloride, where this titanium compound is either covalently bonded or they are occupied a crystal is a crystal position in the lattice of magnesium chloride support. So, that actually helps the activity and the stereospecificity, and sometimes with this sort of trialkyl aluminum chloride or say dialkyl aluminum chloride, sometimes these electron donors are added, electron donors like Lewis acids are added to increase the reactivity and the specificity, stereospecificity of the catalyst. Typically, the activity of the catalyst is measured as a kg of polymer produced per gram of catalyst in an hour, or completely or at the end of the your or for complete polymerization. So, the activity of the catalyst is defined as kg of polymers per gram of the catalyst used. You can use either per hour or at the end of the polymerization. Now, most cases this type of combination of your transition metal compounds and alkyl aluminum compounds, they produce completely isotactic polymers, except few cases where there are few exceptions like vanadium chloride plus trialkyl compound, which gives synthetic. These are exception, a few exception rather than a regular case. Most cases, in almost exclusively all the cases, it is the isotactic which get formed. Now, what is the mechanism? What is the mechanism by which these polymerization happen and stereostacticity is is maintained? There has been lot of studies and lot of mechanism proposed during last several decades, and till there is no mechanism which has been which has been accepted by all the polymer chemists or the scientists working in this field. And so, what happened still this is this Ziegler-Natta polymerization is not completely understood. So, what we will discuss here in this lecture, we will basically talk about two mechanisms. One was proposed originally by Natta, and which is a bimetallic mechanism, and second where majority of has actually accepted this mechanism, which is a monometallic. We will discuss these two in a minute. Now, let us talk about first the bimetallic mechanism. This was originally proposed by Natta himself. Now, in this case the active site is an electron deficient The active site is electron deficient bridged complex formed by chemizoption of the alkyl ammonium, the electropositive alkyl metal alkyl with small ionic radius on the co-catalyst surface. Let us first draw and this is the active site which is electron deficient, and that formed by the chemizoption of the electropositive metal alkyl which has a small ionic radius on the surface of the co-catalyst. Now, once this is formed, which is electron deficient, what happened? The monomer approaches this active site and coordinate. So, we can write the next step. Now, instead of R, we are writing a propagating chain, because that is the steps gets repeated. So, we are not writing the first step, first addition, we are writing any general addition of the next monomer, where P is the polymer residue. And what happened first, the monomer formation of a complex between formation of a pi complex between the with the nucleophilic olefin. This olefin is a nucleophilic. So, and this is electron deficient. So, this approaches and forms a pi complex with the titanium center, which gives you next what happened, this follows by a partial ionization of this olefin as well as this alkyl bridge. So, let us draw that, and there is a partial ionization of this alkyl bridge and also polarization of these monomers, which produce this struck intermediate, which then form a 6-membered ring transition state, which basically form a 6-membered ring transition state. You can draw yourself, and so, that is the 6-membered ring transition state. And what happened now? There is insertion of this new monomer, in the alkyl carbon linkage, alkyl aluminum linkage, and forming again the original titanium moiety, which will now add to the next incoming monomer. So, we have now So, inserting this monomer, new monomer in the aluminum carbon bond, which will form the regeneration of the bridge complex. So, again what happens, next monomer comes and get inserted here, this following the same mechanism, and you get a linear polyolefins in this case. Now, the second mechanism, which is a monometallic, which is proposed by Cauchy and Allman. Now, this case the d orbital, a vacant d orbital present in the transition metal is the main source of catalytic activity, and the chain growth occurs in titanium alkyl bond. In this case, have you seen the chain growth occurs in aluminum carbon bond. In the monometallic case, we are talking about the chain insertion or chain growth happening in the titanium carbon bond, and in this case the vacant d orbital present in the transition metal is the main source of catalytic activity, and as we said that as I said, the insertion happen in between the titanium and carbon bond. So, if we consider the example we given earlier, let us take the same example to get discuss the mechanism. Now, this is a octahedrally coordinated crystal, and because it has to maintain electron neutrality, the titanium at the surface is a 5 coordinated titanium and have a vacant d orbital. And what happened at the beginning, the active center formation happened by addition of a alkyl to this vacant d orbital of 5 coordinated titanium 3 plus. So, there is let me draw that. Now, in this crystal, as I said, this is a octahedrally coordinated. So, at the surface the titanium which is present at the surface is 5 coordinated titanium 3 plus, and that has a vacant d orbital. We are writing this as a vacant d orbital. Now, initially what happened, this alkyl aluminum compound gets chemisorbed in that vacant d orbital and titanium gets alkylated, and this now is a active center. This initiates the polymerization. Let me draw the mechanism in a separate page. So, now we have this vacant orbital, and these are all chlorine, 4 chlorine atoms which are firmly embedded in the crystal of the titanium titanium chloride, again which we are writing the polymer residue here, P as a polymer residue. Now, the monomer gets coordinated from pi complex with the vacant d orbital. monomer gets coordinated to this vacuum the vacant or empty d orbital, and then it forms a cyclic transition state So, it is form a 4 membered cyclic transition state, and then this new monomer get inserted in the titanium carbon bond. In earlier case, in bimetallic case, we proposed the mechanism proposed where the new monomer get inserted in the aluminum carbon bond. In this case, the new monomer is getting inserted in the titanium alkyl bond and regenerating the vacant d orbital. So, CH2CHX, CH2CHX P. Okay. So, now this is this active center is regenerated. So, again one more monomer comes and the cyclic 4 membered cyclic transition formation takes place and the monomer gets inserted in the titanium carbon bond. So, the polymer linear polymerization take place. Now, let us discuss few features of Ziegler-Natta polymerization, which are the mechanism we just talked about, monometallic mechanism. We all talked about that. Let me just summarize one more time the features. This is important mechanism. So, we just one more time let us discuss. So, basically an octahedral vacancy of which is a d orbital of titanium 3 plus is available to complex with the incoming monomer. So, in this case there is a vacant d orbital which is available for complexation with the incoming monomer. The orientation of the coordinated monomer is determined by the steric and electronic interaction with the ligands around the transition metal. So, basically these are the ligands, in this case chloride, their interaction with the monomer, steric and electronic interaction with the monomer actually determine the orientation of the coordination monomers, and the propagation step is completed by insertion of the coordinated monomer in the metal transition metal carbon bond as we discussed just now, and the growing polymer chain is always attached to the transition metal. Remember, in case of bimetallic, the growing polymer chain was attached to the aluminum metal. Now, orientation of the monomer as it insert into the metal carbon bond determine the configuration of the stereo center in the newly formed terminal unit. That is obvious. What is the orientation of the monomer when it gets complex and inserted? That orientation determine the stereo center, whether it will be isotactic or syntactic. And isotactic polymers is always formed when its preferred orientation for coordination is much lower than the other. If one of the orientation is preferred, much preferred, if one of the orientation of this incoming monomer molecules is much preferred over the others, then what happened? The isotactic polymerization formation take place. So, now we basically know this the mechanism of Ziegler-Natta polymerization. So, once initiation propagation is done, let us just glance through the possible mechanism by which we can terminate this Ziegler-Natta polymers or coordination polymers get terminated. And termination actually can happen one of the three ways. One, like I am just doing it little fast. These are nothing more to understand, it is just for information purpose. The termination can happen beta hydride termination to the transition metal. This hydride can get terminated, transferred to the transition metal, forming a vinylidene N group in the polymer. It can also get transferred to a monomer forming this combination. Another way of these polymers, Ziegler-Natta polymers get terminated is by chain transfer to the group 1 to 3 metal alkyl metal, like aluminum alkyl we just discussed. Basically, if you take this example, propylene by titanium catalyst. Now, this can get transferred and you can have the chain get terminated. The chain can transfer to compounds, added compounds which are having active hydrogens. We can write this generic structure of HT where you have a active hydrogen. Then this chain transfer can happen to this and the chain can get terminated. Now, so this is all about the Ziegler-Natta polymerization, and this is the majority of the industrial polymers. In olefinic industrial polymers was synthesized by this catalyst combination, Ziegler-Natta, generic Ziegler-Natta catalyst till the discovery of Metallocene catalyzed coordination polymerization. Now, in case of Metallist, now what I have not talked till now, that this is a heterogeneous polymerization. When you mix this alkyl aluminum and titanium chloride, the catalyst actually get precipitate from the solution, and when you add ethylene or propylene, it is a heterogeneous polymerization. Now, metallations actually you can do the polymerization in homogeneous medium. Metallocene polymerization can be done in solution in homogeneous medium, and the advantage is that at the end of the reaction you can isolate the Metallocene catalyst and then purify and reuse. Now, what is Metallocene polymerization? You can give a general structure of the Metallocene catalyst like this, where or you can write a structure as Al dash MTX2, where Al dash are the ligands which can be equal, but the Al dash can be same or different from different metallocenes like cyclopentadienyl or indenyl or fluorenyl. These are the few examples of the ligand which are present in the metallocenes. For example, ferrocene is an example of metallocenes where you have two cyclopentadiene coordinated with attached with iron. Generally, this metal used is a group 4 transition metal, and in most cases it is zirconium. So, is zirconocene is what mostly used in case of Metallocene polymers, and X is most cases a chloride and sometimes CH3. Now, this is like this titanium transition metal in your Ziegler-Natta polymerization. This requires another co-catalyst like alkyl aluminum as is in the case of Ziegler-Natta polymerization. But if you use alkyl aluminum, then what happened, the stereospecificity was not very high. So, the most used co-catalyst is MAO, which is methyl aluminoxane, which is a network compound of this. Now, for example, let us take a Metallocene polymerization. This is a CP cyclopentadienyl cyclopentadienyl CP2 say titanium chlorides in presence of MAO. MAO does actually does two things. It's alkylate. First, it's alkylate the metal and then abstract one halogen and form metallonyl and which generates one vacant orbital, and rest of the mechanism is same as we discussed in case of Ziegler-Natta polymerization in one, like the insertion of polymer monomer molecules. So, rest of the propagation and propagation stem follow the same similar mechanism as we discussed in case of Ziegler-Natta polymerization. The advantage of Metallocene polymerization is that, as I said, that this can happen in a homogeneous condition, and at the end of the polymerization you can isolate the monomer, isolate the catalyst and purify, and then reuse the catalyst one more time. So, with this we have completed our discussion on stereochemistry, polymer stereochemistry and coordination polymerization. Now, in this lecture itself we basically completed our module on polymer synthesis. What till now what has happened, till these 24 lectures, what except the first few couple of lectures where we give introduction about polymers. The rest of the 22 lectures or 21 lectures we discuss how to synthesize polymers. Now, what are the different ways we can synthesize the polymers, and I try to give emphasis on the polymerization or synthetic process which are important, which are used very frequently or which are more important industrially. And there are some specialized techniques as well where which are used for specific techniques, any technique special polymerization techniques. For example, we solid state polymerization, ring opening metathesis polymerization, or say group transfer polymerization. Now, these are not very common example of polymer synthesis, or a lot of industrial polymers are not used by this technique. So, it can be covered in a specialized course on polymer synthesis itself. So, in a general course like this on polymer chemistry, we are not going in details on this type of specialized polymerization techniques. So, you are requested, if you are interested, you can go and read or consult a specialized book on polymer synthesis to know more about these polymerization techniques. Now, before we end this lecture, let us go through one the commercial few commercial coordination polymers, and you can for example, high density polyethylene which has low branching, high crystallinity, high density. You can actually use these coordination polymers to make high molecular weight, high density polyethylene, or ultra high molecular polyethylene. You can make low density polyethylene as well by copolymerizing with slight amount of one olefin such as 1 butylene or 1 hexylene along very slight amount along with ethylene, that will basically introduce pseudo branches and reduce the crystallization and increase the reduce the density as well. And another very important polymers which is made industrially by this technique is, as we discussed several times, is the polypropylene. And as we said that stereoregular polypropylene like isotactic polymer, polypropylene and synthetic polymers are very useful to synthesize. So, with this we come to end in this module of polymer synthesis. In next lecture onwards, what we will do, we will study the characterization process, how after making these polymers, what are the ways we will characterize and evaluate the polymers, which learned for last 24 lecture, how we have learned how to synthesize those polymers.